Hello everyone, my name is Qi Shen. I'm glad to introduce our paper titled Comprehensive Integration of API Usage Patterns. All the authors of this paper are from Peking University. There are two important concepts in our title, which are API usage pattern and code integration. We will illustrate them with an example, and the example will be used throughout this talk. Suppose we are going to set the background color of Excel cells using existing APIs. By analyzing code examples from the corpus, we summarize a sequence of API method calls to implement the task. Such a frequent API call sequence mined from a corpus is called an API usage pattern. However, the pattern is not the final code. As we can see, the pattern contains 4 missing variables marked with the brackets. The variables need to be synthesized under the user's programming context. This is the integration process of API usage pattern. How to synthesize and recommend the expressions is the research task of our work. To be specific, our task can be described in a formal way. Given a desired type and the current programming context, our task is to synthesize a well-typed expression under the context. For the previous example, the target output of our work is to synthesize an expression for each missing variable in the pattern. To solve the task, we face two challenges. We'll briefly introduce each of them and our corresponding insight as well. The first challenge is how to synthesize all the legal expressions. In this paper, we adopt the type-directed search. As the picture shows, starting from a defined variable from the context, we can expand new variables with method invocations. The expansion stops when the target type is reached. The second challenge is how to rank the synthesized expressions, since the amount could be large. We notice that the variables in an API usage pattern usually have strong dependency. Here's an example. Suppose we need a workbook variable and a sale variable. By analyzing 100 code examples, we find that if we create the workbook from scratch, then the sale is also created from scratch. Otherwise, if we load a workbook, then the sale is highly possible to be loaded as well. In our work, we emphasize such dependency in recommendation by combining user interaction history with the covers analysis. Here is the framework of our approach CODA. It has two parts. In the offline part, we first organize all available code elements for synthesis in a graph structure called API knowledge graph. Then, given an API usage pattern, we call a missing caller or parameter as a whole. We cluster the holes since different holes may refer to the same variable. In online part, for each hole, we first synthesize all the candidate expressions and then recommend them with code examples with similar usage. After users select their desired expression, the recommendation will record the interaction and apply it in the next recommendation. We'll briefly introduce our synthesis and recommendation approach here. More details are explained in the paper. To define the search space for expression synthesis, we design the API knowledge graph. The types of nodes and edges in the graph are summarized from an empirical study. After constructing the graph automatically, we transform the expression synthesis problem to the path search problem on graph. Suppose we have defined a variable with type workbook. A typical path in our API knowledge graph is a method call sequence. In this example, each path from the root to the leaf corresponding to a well-typed expression. By collecting all the paths under a length restriction, we can get the complete set of well-typed expressions. The next step is to design a ranking function to rank and recommend them. Our ranking strategy considers two metrics. The first one is completeness. During the process of synthesizing expressions, it may bring new undefined variables like parameters. We encourage our approach to return complete expressions than incomplete ones. The second metric is popularity in the corpus. Notice that our corpus is dynamically updated in the integration process. After the user selects an expression, examples with the same behavior will be promoted, while unrelated examples will be removed. Here's the evaluation part. We evaluate CODA with two research questions. The first question gives a feeling of CODA's ability to recommend related code examples. We collect 93 API usage patterns from the official tutorial of 3 Java APIs. For each pattern, we specify a code example as a target one and simulate the user interaction to check whether the target example can be recommended. The second question evaluates Coda's usefulness in real-world development. We invite developers to integrate 5 code fragments from Stack Overflow with Coda. This is the result of our evaluation. For question 1, we find Coda can filter 90% unrelated code examples in the corpus in 3 user interactions. After the user finishes the interactions, the target example is ranked in the top 5 of 100 code examples. For question 2, we record the ranking of the correct expression in each recommendation and display it in the MRR metric. The average MRR value shows that the correct expression is often recommended in the top 2. By comparing Coda with a popular code completion tool, Codota, users with Coda in our experiment can save 30% time. In this talk, we introduce Coda, an interactive method to support API usage pattern integration. The idea of Coda's integration is twofold. First, it synthesizes all candidate expressions by searching our API knowledge graph. Second, it recommends the expressions considering both their completeness and fitness to the user interaction history. In the future, besides keep improving Coda's performance in real-world IDEs, we are now focusing on combining Coda with API location techniques and API usage pattern mining tools. We hope to build a big picture to help users integrate APIs after searching and learning them. That's all the content of my talk. Thanks for your listening. If you are interested in our work, please feel free to try our web demo and contact me.
If you don't have... Okay, I have one question. In the evaluation result, tasks Q3 and Q5 indicate a relatively lower MRR than other tasks. Can you share your thought regarding this result?
Excuse me, I didn't really catch it. So, do you mean Do you mean the question 4 and 5 in our second experiment?
No, the task in the research question 2, tasks Q3 and Q5 have a lower MMR score.
Okay.
So, especially the task Q3 have a lower MRR score.
Oh, okay, I understand.
So
you mean the MRR metric in for question 2 and question 3?
Yeah, question MRR score regarding the task Q3 is very low, right?
Oh yeah.
So why?
Because I think our synthesizer, you mean our basic story is that you're given a usage pattern and then you need to integrate into your local context. For question 3, we need array operation to fill one parameter that is out of scope of the ability of our current synthesizer.
So also the question 5 is also relatively lower because the MRR score was maybe 0.5 or something.
Actually, in our experiment, our synthesizer can recommend the desired expression in top 2, and so we did not really think that the 0.5 is a very, very low MR metric. Yeah.
Oh, I see. Okay.